Episode 5, Late Heavy Bombardment. Look up at the moon tonight. If the sky is clear, look at those dark patches. The meridian, the lunar seas that ancient astronomers thought were bodies of water. Look at the bright, cratered highlands. Every crater you see, from the largest basin visible to the naked eye, to the smallest pockmark visible through a telescope, tells a story of violence. Each one marks where an asteroid or comet struck the moon's surface, traveling at thousands of miles per hour, releasing energy equivalent to nuclear weapons. The moon is scarred. Its face is a record of bombardment of cosmic projectiles that have been raining down since the moon formed 4.5 billion years ago. But look more closely at those craters and you will notice something interesting. Many of them overlap. Many of them are degraded, worn down by the later impacts. But the largest basins, the great circular area, like Mare Imbrium and Mare Serenitatis, are relatively fresh. They appear to have formed after the initial heavy cratering during a specific period of intense bombardment. This observation, made by lunar scientists studying the rocks brought back by the Apollo missions, led to a startling conclusion. The moon, and by extension Earth, experienced two distinct phases of bombardment. The first phase was during and immediately after planetary formation, the tail ends of the planet building process, which we have discussed in earlier episodes. But then, after a period of relative quiet, there was a second surge of impacts, a cosmic assault that lasted perhaps 100 million years or more. The second phase is called Late Heavy Bombardment, and it may have been the most significant event in Earth's early history. After the Theia impact, it may have delayed the origin of life, or destroyed early life and forced it to begin again. It may have delivered water and organic compounds that made life possible. It reshaped Earth's surface, vaporized its oceans, and tested the young planet's resilience to the breaking point. This is the story of that bombardment, of what caused it, what it did to the Earth, and how our planet survived. To understand the late heavy bombardment, we need to understand the architecture of the early solar system and the forces that shaped it. When the planets finished forming around 4.5 billion years ago, the solar system was not empty as it is today. Beyond the orbit of Mars, in the region we now call the asteroid belt, there were countless planetesimals, rocky bodies that had never quite managed to assemble into a planet, preventing from doing so by the gravitational influence of nearby Jupiter. The further out beyond the orbits of the giant planets, Jupiter, Saturn, billions of comets orbiting the cold darkness. Some of them occupy the region we now call the Kuiper Belt, a disk of icy objects beyond Neptune. Others who were even farther out in a spherical cloud called the Oort cloud, extending halfway to the nearest star. For the first few hundred million years after planetary formation, this architecture was relatively stable. The planets occupied their orbits. The asteroids and comets stayed in their respective zones. Impacts on the inner planets decreased as the local supply of projectiles was exhausted. But then something happened. The orbits of the giant planets began to change. This might seem strange. We think of planetary orbits as fixed and eternal, but they're bodies. But they're not. Planets interact gravitationally with one another and with the swarms of smaller bodies in the solar system. These interactions over time can cause orbits to migrate, to shift inward or outward, to change shape and orientation. In the early solar system, these interactions were particularly strong because there was so much debris, so many planetesimals and comets that could interact with the planets, and the giant planets, with their enormous masses and gravitational influence, were the primary drivers of change. The grand scientific model for what happened is called the Nice model, named after the city in France where it was developed. Not because it is pleasant. The Nice model proposed that the giant planets initially formed in a more compact configuration than they occupy today, with Jupiter, Saturn, Uranus, and Neptune all closer together and closer to the Sun. For some time, this configuration was stable, but the planets were embedded in a disk of planetesimals, and as they interacted gravitationally with these objects, scattering them inward or outward, the planets themselves began to migrate. Jupiter, the most massive, migrated inward slightly. Saturn, Uranus, and Neptune migrated outward. This migration was gradual at first, but then, somewhere between 4.1 and 3.8 billion years ago, the system became unstable. The orbital resonances between the planets, the mathematical relationships between the orbital periods shifted, and when this happened, chaos ensued. Neptune and Uranus may have switched positions, or their orbits may have become slightly eccentric before settling down again. Saturn may have moved outward rapidly, escaping from a resonance with Jupiter, and as these giant planets careened through the outer solar system, their paths took them through the disk of icy planetesimals that had been peacefully orbiting beyond them. The result was a cosmic billiard game of unimaginable scale. The giant planets scattered the icy planetesimals in all directions. Some were flung out of the solar system entirely meteors were thrown into the inner solar system, crossing the orbits of the terrestrial planets, bombarding Mercury, Venus, Earth, and Mars. At the same time, the shifting orbits of the giant planets destabilized the asteroid belt, sending asteroids careening into the inner solar system as well. This was the late heavy bombarding, a storm of asteroids and comets, numbering in the billions, raining down on the inner planets for tens or even hundreds of millions of years. The moon, with no atmosphere or geological activity to erase craters, bears the scars to this day, and Earth, though its craters have been erased by erosion and plate tectonics, was hit just as hard, if not harder, given its larger size and greater gravitational pull. Let us try to imagine what this meant for Earth. By the time the late heavy bombardment began, Earth had been settling into a relatively stable state. The ocean had formed, and it had persisted for perhaps a few hundred million years. The crust had thickened and stabilized. Volcanic activity, while still vigorous, was less chaotic than it had been in the Aegean. The atmosphere had a relatively consistent composition, thick with carbon dioxide and nitrogen, but stable, and it is possible, though not certain, that the life had already begun. Some evidence, which we will discuss in a later episode, suggests that the first living organisms may have appeared as early as 4.3 or 4.2 billion years ago, in the quiet period before the late heavy bombardment. If so, that early life was about to face its greatest challenge. The bombardment began gradually, with the impact rate increasing over time as more and more objects were scattered into the inner solar system. At first, the impacts may have been no more frequent than they had been in the preceding 100 million years. Perhaps a larger impact every few thousand years, with smaller impacts more frequently. But as the giant planet migration continued and more objects were perturbed from the stable orbits, the impact rate increased. A large impact every 1,000 years, every 100 years, at the peak of the bombardment. There may have been multiple large impacts per century. Objects tens or hundreds of miles across, striking Earth with the force of millions of nuclear weapons. Each impact was a local or global catastrophe, depending on its size. A small impactor, a few miles across, would create a crater tens of miles wide, blast rock and debris into the atmosphere, trigger earthquakes and landslides, and possibly generate tsunamis if it struck the ocean. The dust and soot thrown into the atmosphere would block sunlight, cool eruptions and earthquakes worldwide. Debris would be blasted into space, some of it falling back to Earth in a rain of molten rock that would heat the atmosphere to hundreds of degrees, perhaps even to temperatures high enough to boil the ocean. The very largest impacts from objects 100 miles across or larger would be extinction level events. They would vaporize significant portions of the ocean, blast away parts of the atmosphere, and melt or vaporize large sections of the crust. The entire surface of the planet would be rendered uninhabitable for thousands of years, and there may have been dozens or hundreds of such large impacts during the late heavy bombardment. Models suggest that the moon alone was struck by perhaps 40 or 50 objects large enough to create the great impact basins we see today. Basins hundreds of miles across, Earth with 8 times more surface area of the moon and greater gravity would have been struck proportionally more. Think about what this means. Every few million years, on average, a cataclysmic impact. Every few 100,000 years, a major impact. Every few thousand years, a significant impact. For 100 million years or so, if life existed before the late heavy bombardment, it is hard to see how it could have survived on the surface. The repeated sterilization events, the vaporization of the ocean, the melting of the crust, all would have destroyed any organisms living in the shallow water or on land. But there may have been refugees deep in the ocean, far from the surface, organisms living near hydrothermal vents might have survived. These vents, cracks in the seafloor, where hot water from the Earth's interior mixes with the cold ocean water, creating chemical gradients and providing energy for chemosynthetic organisms, bacteria, and archaea that derive energy from chemical reactions rather than sunlight. These deep-sea organisms would have been insulated from the worst effects of the bombardment. Even if the surface ocean was boiled away, the deep ocean would have remained protected by miles of water and rock. Hydrothermal systems would have continued to operate, fed by heat from Earth's interior, unaffected by impacts on the surface. Similarly, organisms living deep underground, in cracks and pores in the rock, miles below the surface, might have survived. The subsurface biosphere, as we call it today, is vast, containing perhaps as much biomass as the entire surface biosphere. If such an ecosystem existed in the deep past, it could have served as a refuge during the bombardment. This leads to an intriguing possibility. Perhaps life originated not once but multiple times during Earth's early history. Perhaps it appeared on the surface, was destroyed by an impact, appeared again, was destroyed again, multiple cycles of origin and extinction, until finally it took hold in a deep, protected environment asteroid belt was cleared of most of its larger members, leaving only the relatively small population of asteroids we observe now. The Kuiper belt and Oort cloud, depleted by scattering event, became quiet. By about 3.8 billion years ago, the late heavy bombardment was over. Impact continued and still continued to this day, but at far lower rates. The inner solar system had been swept clean. Earth could finally develop without being repeatedly sterilized, and it did within a few hundred million years. After the bombardment ended, there is clear evidence of life on Earth. We will discuss this evidence in the future episodes. But the timing is suggestive. Once the bombardment ended, the life flourished. Whether it was emerging for the first time or recovering from near extinction, we cannot say. But the correlation is clear. The late heavy bombardment shaped Earth in other ways as well. The countless impacts delivered enormous amounts of material to our planet. Some of this material was rocky, adding to Earth's mass, but much of it was ice. Comets from the outer solar system, each containing vast quantities of water and organic compounds. This raises an important question that we touched on in the previous episode. How much of the Earth's water came from comets delivered during the late heavy bombardment? The answer is complicated. Isotopic studies of Earth's water, comparing the ratio of deuterium, heavy hydrogen, to normal hydrogen, suggest that the most of the Earth's water does not match the isotopic composition of the comets we can observe today. Earth's water is more similar to the water in asteroids from the outer asteroid belt, suggesting that most of our water came from rocky asteroids rather than icy comets. But this doesn't mean comets contributed nothing. They may have delivered a significant minority of Earth's water, and they almost certainly delivered organic compounds, the carbon-based molecules that are building blocks of life. Comets are rich in organic material, and every comet that struck Earth during the bombardment added these molecules to the primordial soup. In a sense, the bombardment was both destroyer and creator. It sterilized the surface repeatedly, making life difficult or impossible. But it also delivered the raw material for life, the water and organics that made the origin of life possible. Once conditions stabilized, this duality, destruction and creation, is a recurring theme in Earth's history. Catastrophes that seem to spell doom for life, often in the long run, create opportunities. Mass extinctions open ecological niche for the new species to evolve. Volcanic eruptions, devastating in the short term, add nutrients to the soil and gases to the atmosphere that support life, and the Some scientists have proposed that the late bombardment helped to kickstart or accelerate plate tectonic activity, the recycling of Earth's crust that is so important for regulating climate and providing nutrients for life. The bombardment also affected the moon in ways that influenced Earth. The large impacts that created the lunar marea blasted enormous amounts of material off of the moon's surface. Some of this material fell back to the moon, but some escaped the moon's gravity and either fell to Earth or it was lost to space. Earth and moon in this period were exchanging material linked by the impacts that scarred both worlds. As we close this episode, let us reflect on the resilience of Earth. Our planet has endured catastrophes that would have destroyed lesser worlds. It has been struck by objects that vaporized its oceans, melted its crust, and blasted away its atmosphere, and yet it survived. It cooled, it reformed, it became once again a world with oceans in a stable climate, a world ready for life. As we close this episode, let us reflect on the resilience of Earth. Our planet has endured catastrophes that would have destroyed lesser worlds. It has been struck by objects that vaporized its ocean, melted its crust, and blasted away its atmosphere. And yet it survived. It cooled. It reformed. It became once again a world with oceans and stable climate. A world ready for life. This resilience is built into the nature of planets. They are massive, held together by gravity, thermally buffered by their huge heat capacity. You cannot easily destroy a planet. You can scar it, sterilize it, transform it, but short of physically shattering it into pieces, it will persist. You can scar it, sterilize it, transform it, but short of physically shattering it into pieces, it will persist, and over time it will heal. Earth's healing after the late heavy bombardment was relatively rapid on geological timescales. Within a few million years, after even the largest impacts, the ocean would have recondensed from the steam atmosphere. With a few tens of millions of years, the crust would have solidified and cooled. Within 100 million years, there would be little surface evidence that the catastrophe had occurred at all, save perhaps for a few exceptionally large craters or impact basins. But the effects of the bombardment would echo through Earth's history. The materials delivered shaped our planet's chemistry. The heat and the shock of the impacts may have influenced plate tectonics and volcanism, and if the bombardment did destroy early life, forcing it to begin again in protected deep environments, it may have shaped the course of biological evolution in ways we are only beginning to understand. By 3.2 stability compared to what had come before. The oceans were permanent. The crust was solid and thick, and volcanic activity continued, but was not overwhelming. And in this newly stable world, life had either survived or emerged for the first time. The stage was set for the next great chapter in the Earth's history, the rise of the first true organisms, the bacteria and archaea that would dominate the planet for the next 2.5 billion years, and that continue to shape our world today. But before we turn to the story of early life, take a moment to appreciate the journey we have witnessed so far, from a cloud of gas and dust to a molten ball of rock to a planet with oceans and continents, from the chaos of planetary formation through the violence of the impact and the devastation of the late heavy bombardment. Through it all, Earth has persisted, changed, adapted. We are the inheritors of this long history. We live on a world that has been tested by cosmic violence and has emerged not unscathed but intact, a blue oasis in the black void of space, the greatest ever rotted away. But the lessons remain. Earth is resilient, but not invulnerable. It had survived catastrophes before, but each one has changed it, shaped it, directed its evolution. As we look to the future and consider the changes we ourselves are imposing on our planet, it is worth remembering this history. Earth will survive it, as it survived the late heavy bombardment. But the Earth that survives may be very different from the Earth we know, and whether it remains a hospitable home for life and for humanity depends on choices we make today. In the next episode, we will turn to one of the greatest mysteries in science, the origin of life. We will explore how chemistry became biology, how non-living molecules organize themselves into the first cells. We will see life's first spark in Earth's ancient oceans, and we will begin the story of evolution, the progress that would transform a world of bacteria into a world of dinosaurs and humans, and all the incredible diversity of life we see today. The bombardment is over. The surface is calm,